Hello student, how are you? I hope you all are happy, healthy and fine at home. So what did we discuss yesterday? Yesterday we discussed about the discovery of this carbohydrate in a natural product. So that type of the thing we have seen. So today what we are going to learn about one important point, that is the rule of 5, the hydroxyaldehyde or the ketone connection. What is that? What is that rule of 5? How we can recognize, or what does it mean? For example, we know that the carbohydrate type of the if you look at as a sugar is there, sugar means specifically for D-glucose there is a carbon atoms are the 5-membered ring are the open chain rings, and how they are how to recognize the carbon skeleton or that much segment, so that is known as a rule of 5. In the position of a ring, the position of the ring oxygen and anomeric, and you know that the anomeric carbon, do you know that anomeric carbon means what? Where the carbon number 1, where the what we can call it as it has different configuration than the other one. For example, glucose and mannose, they are differ from each other, so that type of the carbon number 1 is called as the anomeric carbon. Means at one carbon atom there is a different configuration. Means suppose as a R configuration, another should have a S configuration. The type of the center is known as an anomeric center. While studying as a carbohydrate chemistry, we will see the details of this, but here just remember they are differ by their configuration. One is showing as R configuration, another showing as a S configuration. That center is known as a anomeric position. And rule of 5 means what? The position of a ring oxygen and anomeric carbon in hexapyranose derivative are 5 atoms are bonds away. This is called rule of 5. For example, is a ring form is there. Suppose there is a ring form is there like this, and they are OH is there. So they are 1, 2, 3, 4, 5, and this is called as an anomeric carbon atom, and they are away the 5, and that type of the thing is called as a 5. Means hydroxyaldehyde or the ketone connection, because this is the oxygen which is coming from either from aldehyde or the ketone, so that type of the thing is called as a rule of 5. Or we can draw this type of the structure, longest structure there, C double bond O, H aldehyde, and here maybe as a HO. Means 1, 2, 3, let us see, I think one more carbon atom, maybe here you can write as this one, 1, 2, 3, 4, 5 carbon atom. When we form as a ring with this, so that becomes as a 5. So that rule is known as a rule of 5. In a large number of synthesis based on carbohydrate precursor, the chiron is derived from the cyclic derivatives. Chiron is derived because by using that chiron, ultimately you will get the chiron is nothing but as a intermediate, and so that treating with some reagent you are going to get as a final target molecule, and that chiron which is obtained from the precursor or the template which are naturally available, and so that is it. And hence the relationship of heteroatom substituent, and particularly the ring oxygen atom to the anomeric carbon, formally an aldehyde or the ketone, formally aldehyde or ketone, is important in locating the carbohydrate portion in the target molecule, and that's why it is known as a rule of 5. A simple protocol consists in establishing the spatial relationship between carbon atom bearing an oxygen or the other heteroatom and a given carbon atom located 4 or 5 atom away along the chain or ring, and this set up series of at least 4 or 5 consecutive atom, 4 or 5 consecutive atom in which an sp2 or sp3 carbon, for example, may correspond to the anomeric carbon and the heteroatom containing the carbon to C4 or C5 in a furanose-pyranose derivative respectively. And the possible functional overlap of the carbon framework of a suitable carbohydrate with a segment of a target structure regardless of configuration is the found, and substituent present in between can be introduced by systematic manipulation of the hydroxyl group, including eventually the ring oxygen. Of course, this protocol does not preclude the utilization of carbohydrate as a precursor to target or segment of target which are derived of heteroatom. In such cases, the carbohydrate chain must be extensively deoxygenated and predisposed center replaced by the heteroatoms, carbon substituent, etc., based on the notion already developed. And the disposition of ring oxygen of the another anomeric carbon in a hexapyranose derivative, for example, is 5 atoms or bonds away, and a rule of 5 can be arbitrarily advanced. Such a rule is applicable to a large number of recorded syntheses, even if in retrospect the connection not evident at the inspection of the original plan, and it may indeed help in the planning of future synthesis from carbohydrates. Let us see how this is applicable or applied in an illustration of how this rule, means carbon 5 rule, can be used in locating potential and as we know that carbohydrate is a potential type, carbohydrate type symmetry in metacine, one of the natural product or the drug, by performing bond disconnection that generate 6 carbon segment is shown below, and that explain how it is applicable, where that rule of 5 is applicable in this case, that is shown over here. Let us see as a structure of metacine. The structure of metacine is this one. This is a structure of metacine. Here is a benzene ring, and benzene ring containing here is a chlorine atom, and then here is a N methyl group, then there will be carbonyl group, then this one. The structure is a very big one, so epoxide formation, and then there will be this one attached, and then there is this ring. Here may be oxygen atom over here, and then there is that is Lect-10 type of the ring, and here again is a nitrogen atom, then nitrogen atom, and next one is this double bond, then this, one more double bond, then this one attached to this one. This is a big structure over here. See, here is a methyl group. At this junction there is nothing but here dash dash OR alkoxy group. At this position there will be a methyl group, and at this junction hydrogen atom is there, and here again is a methyl group, and here is again OH group. At this junction there is OMe group which is below the plane, and at this carbon atom nothing is there, and here is a methyl group. Now they have given the number to this carbon atom. Starting from here they start the carbon number 1 2 3 4 5 6 7 8 9 10 11 12 13 14, and this one is a 15. That is a carbon chelator. So 15 are there. So how we can apply the rule of 5? This is one of the best example. This is a target molecule is given, and the name of this compound is a mystacine. Metacine. This is the name of this molecule. This is one of the complex molecule. How we can recognize, how we can apply the rule of 5 for this target molecule, that we are going to learn over here. Here is a H, and what is that? NMeOR. Here this R is taken as, R is nothing but this one, I think CO, then CO, CMe, then HN, there will be here AC and methyl group. There is a tertiary groups are there. So this R is nothing but as this one. So this is the biggest molecule, and how they apply, how we can apply the rule of 5 over here, that we are going to learn. So let us see here the one of the segment. Suppose this one, C double bond O, then here is a OR, then there is a epoxide, and then this one. You can look from this side. If you number these carbon atoms, it is 1 2 3 4 5 and 6 over here, 5. So this is a rule of 5, means look at this skeleton from here, here, and here. You look from this side, so there will be a 5 carbon atom, means that segment which is coming from the carbohydrates. So there is a C1 carbon changes to C6, right? C1 to C6. This is one of the segment from here 1 to this C6 is a skeleton. That segment is there, and now this is one of the segment. First segment. Now second segment will be like this. So this side is a other part, right? That other molecule from this side and that side also. Now here this side and this side there is a C1 and C6 segment. Now let us look at here. There is carbon-carbon double bond. This, then this one, and now this, and here is a oxygen atom. Then you can put this one. So this segment has, there is a, here you can write Y, and here is a OME, and the number from here, from this side, 1 2 3 4 5. So you can look from this side only. Look, this is a segment. This is again application of that C6 to C11. This is a C6 changes to C11, C6, from this to this one. So this is C6, this is a segment, and that are the compound. Now this is about the segment. Now third segment may be as a this one. You can draw. I am showing here. There is no space. There oxygen, then 2 OR, right? Not this epoxide, not this one. There is a segment O. After that, this one O. So we can give number from his 1 2 3 4 and 5. At 5 you can look from this side, look from this side, and this is a 6 one, and this is a compound, segment number 3. So C3 to C8 segment, C3 to C8 segment, up to this segment, that is a carbohydrate. You can look from here to here. This segment is there, C3 to C8, or there may be another segment where we can use segment C9 to C14, C9 to C14. Look at here carefully, C9 to C14, and this is one of the skeleton or the segment. We can see this is another segment, C9 to C14, C9 to C14, similar segments are there. Then C6 to C11, C6 to C11, this is one of the segment. You can clearly look at here, one segment over there, and finally C3 to C8, C3 to C8, this is one of the segment present over there. So that type of the rule. But here the chiral template, what type of the chiral template is present over here? These are the segment, or this is the application of this rule. The chiral template may be as this one that we are getting here. Suppose as this is anomeric carbon 1, and here you can write A, then B, and here C. This is carbon number 1 2 3 4 and 5 here, and here may be as this one is a 6 one. So this is a chiral template. This is a chiral template present over here, and this are in what we can call it as this chiral template may be present over here. And now we can, this chiral template, we can see this is nothing but we can write in this way. Let us see here properly. We can draw here. Let me clean the board first. Just now we have seen how we can apply here. There is a this. There is a OH at this side. Then here C, here B, here A, and it may be as this one, right? So numbering start from here 1 2 3 4 and 5, and this may be as a 6 one. So this is nothing but as a chiral template, or the precursor, how it is applied or how it is useful used as a rule of 5. This is explained with this example. So each of these segment comprise a formal 5 oxygen atom with a predetermined sense of chirality, and anomeric chiron indicated as a potential hexose precursor for synthetic purpose to the choice of a particular segment. The generation of a chiron and its synthesis from an appropriate carbohydrate is another operational convenience, and rather consideration should be given to the nature, the location and the stereochemistry of substitution along each chain, and the prospect of achieving maximum chiral and functional overlap by the most efficient route from a given carbohydrate, that is D or L. We already know that capital D and L are used for relative configuration, and cyclic sugar derivatives can be functionalized at predetermined site based on the consideration of steric control, conformational bias, stereo control and stereoelectronic control, and modified derivatives are then converted into other cyclic or acyclic derivatives which could coincide with the target structure or a portion of it, and further manipulation may be necessary to assemble the entire molecule. And location of hidden carbohydrate type symmetry in meta sign application of the rule of 5, and note 2 reference point in the target the carbon atom overlap with the anomeric carbon atom of the carbohydrate, and number 2, a heteroatom, oxygen, nitrogen or sulfur etc., located 5 bonds away from the sp2 or sp3 carbon atom overlap with ring oxygen, and number 3 now is a functionalization and the control of stereochemistry by manipulation of hydroxyl group. Now we are going to learn how the functionalization control of stereochemistry by manipulation of hydroxyl group, that we are going to learn here. Whatever we have seen over here just now is a, what is that, 5 rule. Now rule of 5 we have learned, and with the example in the, I think let us stop today here. Next time what we can next time we will learn about the functionalization and control stereochemistry by manipulating hydroxyl group. How we can manipulate that one, that we will see in the next lecture. Let us stop today here. Thank you. Have a nice day.